So you now know what the inverse matrix and inverse transformation is, and you even know how to obtain it for some simple cases where you can just think for a while and get it. But can you calculate the inverse of any matrix whatsoever? Is there a recipe to do it? So let's look at the recipes. So for a 2 by 2 matrix, let's call it A equals A, B, C, D. The inverse matrix is really easy. The inverse matrix is equal to 1 divided by the determinant of A, which if you remember was A times D minus B times C, times this matrix, D minus B minus C, A. This is the general recipe for the inverse of a 2 by 2 matrix. Simple, right? I encourage you to check that in the two examples we did previously, the scaling and the rotation, you can apply this formula and you get the inverse. What about in general for a n by n matrix? So in this case, so let's say so it has n rows and n columns, yeah? So it's an n by n matrix. So the inverse of A is given by the matrix of the cofactors transposed divided by the determinant of A. Now, if you remember, the matrix of the cofactors is something you saw when we were studying the calculation of determinants in the Laplace expansion. Yeah, and actually you saw that the cofactors, the elements of the matrix, the I column and the jth row, the ith row and the jth column of this cofactor matrix is equal to minus 1 to the I plus j times the minor for that element. And the minor for that element was the determinant that you find when you cross out the row and the column. Yes? So this is it. This is the recipe for the inverse for any size of matrix. Yeah? So let's see an example. So find the inverse matrix for this matrix here. How do we start? Okay, let's start by calculating the determinant. So we can do the rule of Sarus, for example, or even better, we can notice that this matrix is a triangular matrix. And remember, when you have a triangular matrix, the determinant is just the product of the elements of the main diagonal. Therefore, determinant of A is equal to 1 times 1 times 2 equals 2. And this is true because it's a triangular matrix. So we have the determinant. Next, we need the cofactor matrix. And for that, we need the minors. Okay, so let's start by calculating the minors. So second step, calculate the minors. Okay, so for this, let me draw the matrix here again. And we need to find 9 minors. So we find 1 minor for each element. Yeah. So the first minor is equal to the determinant that you get when you cross out the first row and the first column. So we look at what remains, which is this. So we need to find the determinant of 1 minus 1, 0, 2, which is equal to 1 times 2 minus 1 times 0 equals 2. So that's the first minor. For the second minor, for this one corresponding to this element, we cross out that row and that column, and we are left with the determinant of 0, minus 1, 0, 2. And this determinant is 0, minus 0, 0. Now, for this third element here, the minor 1, 3 equals the determinant of which matrix? The one that is left when we cross out this row and this column. So it's the determinant of this matrix 0, 1, 0, 0, which is equal to 0. Next, we look at this element here. So we cross out this row and this column. And this is the determinant of 2, 0, 0, 2, which is equal to 4. And so on, okay? So let me just write it quickly. Done. We calculated the 9 minors. So good luck that this was a 3 by 3 matrix, because if it were a 4 by 4 matrix that you were trying to calculate the inverse, each of the minors would be a 3 by 3 determinant. Yeah. So imagine how long it can get. But okay, we have the minors. So our matrix of minors is the following matrix: 2, 0, 0, 4, 2, 0, minus 2, minus 1, 1. Next, we calculate the matrix of the cofactors. And remember, the matrix of the cofactors was simply equal to the matrix of the minors, but changing the signs in a chessboard-like pattern. So let's start. Let me copy the minors here. And now I'm going to change the sign. So we start with a plus sign on the top left, and then we change the signs like this: minus, minus. This one stays the same. We change this one to a plus, and this one to a minus. Yeah. So we change the sign of these elements. So therefore, the matrix of cofactors is simply the one I have written there. Yeah. So what is the matrix of the cofactors transpose? Okay, I simply have to switch the columns to the rows, or equivalently, I imagine there is a mirror here, and I simply do the mirror reflection of that. Yeah, so I get 2 minus 4 minus 2, 0, 2, 1, 0, 0, 1. And that is the cofactors matrix transposed. So finally, we can apply the recipe for the inverse, which is the cofactors transposed divided by the determinant. So the inverse matrix of A is 1 divided by the determinant, and the determinant was 2, times the matrix of the cofactors transposed. And that solves the problem of the inverse of a matrix.